We're at the Chit Chat Cafe in Pacifica, California, November 25th, 2013. And the experiment is working. I've been running it earlier. I took a background. I'll explain it all later, but I took all the numbers so I don't have to bore you with the numbers later. So it's about the wave-particle duality paradox for matter and light. So I'm going to explain each of these words so we know just what we're talking about. Wave, what's a wave? Well, a wave goes everywhere. It does not hold itself together. So the most important thing is to distinguish between what's a wave and what's a particle. A particle will hold itself together. Now, particle does not necessarily mean matter or light. It's just about whether it holds together, because there are models of particles applied to matter and light. And that's what this talk is about. So that's waves. They spread out. Particles don't. Duality is about the mixture of these two ideas. The wave idea and the particle idea are mutually exclusive. You don't really, you don't make waves out of, waves don't act like particles and particles don't act like waves. Internally, you could have a particle that's maybe a wave, but that doesn't matter. The problem is, in quantum mechanics, they do mix the two ideas together in a way where you have to give up how that could possibly be. And they know that, because that's what gets into the weirdness. That's why there is this weirdness of quantum mechanics. It's about wave-particle duality, and there's no way of picturing how that could happen. The wave model and the particle model are really mutually exclusive. But they tell you it works that way anyway. They'll insist that that's what's going on. And I'll show you that. Paradox. It's something that seems true but may not be true. It's a real problem. I'm dealing with both matter and light. Light has the paradox. It can act like a wave or a particle, so they say. Matter also has this problem. But I claim to be resolving all that with this experiment and the historical analysis and the theory that I'm just going to try to outline, because it's a lot of material. It may be difficult material. So I'll do my best. And please ask questions or make comments if there's anything you don't understand, because I'm trying to win friends here. And move closer if you like. So I put together this cartoon as to how to see what's going on with this wave particleness without the paradox. It's called the double slit experiment, and usually they'll explain waves going across space, and then they'll have a particle going across also, and that will make some event that... So let me draw the double slit experiment. So there are places where the waves reinforce, and there are places where they cancel out. So where they reinforce, there's going to be a lot of events, and then there'll be little, and where they cancel out, there won't be anything. And here they have a weak source of light, or it could be electrons. Usually it's light. They'll say it emits one photon at a time, and you can tell that. So even with this weak source where there's one at a time, there are these events that happen, and they'll say, oh, a particle hit there to make that event. But it all shows up in this interference pattern where some places it cancels out and some places it doesn't. And that can only be explained by waves because it has to go through both paths. That's the paradox. The double slit experiment is a statement of the paradox. So what I'm saying is really happening is that it's not particles at all that hit there, is that it's a threshold effect, where if you were to picture it like I drew wine glasses, where someone's singing and it builds up its energy and it rings until it breaks. Now, if you didn't see the sound going across space, you'd say a bullet hit there and made it break. But it was just waves. So you can picture this wave-particle effect with just waves and threshold effects. And that's what I'm saying is going on. Now, so it's called the loading theory, where the energy loads up. It builds up to a threshold. And when it builds up, it could all escape at once. It's a system of continuous absorption and explosive emission. This idea is old. It was worked on since 1900 by, in 1911, Planck worked on it. It's actually Planck's second theory. Sommerfeld and Debye worked on it. Several great names worked on it, but they didn't like it for some reason. They didn't understand the preloaded state. In fact, I have with me books that talk down about the loading theory, so you don't even have to believe me. I can show it to you afterwards. They explain the loading theory in our textbooks without a preloaded state, to where it always has to be loading up energy from the bottom, and they say, oh, well, it takes too much time for it to do that. And so it can't do that. So you calculate time, the time for a photoelectric effect. So you see that in our textbooks. And here, you won't be able to read that, but I just put 3 textbook examples, just excerpts there. They give this homework problem or example where they say, calculate how much time will it take in the photoelectric effect to respond. And you get some number of seconds, like a minute. And then they'll say, oh, well, there was this experiment done in 1928 by Lorentz and Beams, and they say, oh, well, it responded in a nanosecond or a few nanoseconds. And they say, well, it can't possibly be the loading theory. This is in our textbooks. And I'll show it to you right here, where they do this. But they made a big mistake. They're comparing a total time to load up with a minimum time. The 1 nanosecond is the shortest time in response to the photoelectric effect. When you calculate it, it's the longest time. So the textbooks are playing this trick on us to teach us that the loading theory is not possible. This is only one example of misrepresentations of the history of physics and experiments that they've done to make it look like quantum mechanics has to be true. Now, there are many people who've argued against quantum mechanics, but I'm different because I have an experiment that shows where quantum mechanics fails. And as far as I can see, no one else has ever done that. That makes this very unique. These events that I'm talking and demonstrating, it's just never been done by anyone else to violate quantum mechanics. It's a big deal. So I'm going to explain this experiment. It's about that by the photon model, it should only go one way or another at a beam splitter. So it's a beam split experiment. First, First, let's get straight that they really think it's photons. This is from Wikipedia Photon. This is not a special case. They all talk like this. So they're talking about, well, can it be really? And then they say, yeah, all semi-classical theories. Semi-classical means it's not quantum mechanics. All semi-classical theories were refuted definitively in the 1970s and 1980s by photon correlation experiments. They give a note of certain references, and I'll show you those references. Hence, Einstein's hypothesis that quantization is a property of light itself is considered to be proven. So that's what we're talking about here. The experiment is about, is light quantized? If light is quantized, if it acts like a particle, it should only go one way or another at a beam splitter. So let's see the beam splitter. Let's see what this is. There it is. All right. This is how other people did the experiment. They have a source that's one at a time, and you can do that. So I'm saying it does emit. The emission is Planck's constant h times the frequency is an energy. Now, they'll say that's the photon energy, but I don't want to use the word photon because I'm disproving the photon model. So I'm just going to call it an HF. So I agree that, yes, an HF is emitted, but thereafter I'm saying it spreads classically and showing that it had to be that way. But they don't think it spreads classically. They think it's quantized on emission. Quantum mechanics says light is quantized on emission and absorption. What I'm saying is that light is quantized on emission but not absorption. I'm saying it's continuous absorption. That's the difference between what I'm saying and what everybody else is saying and what the experiment is about. Yes? Quantized is units of HF. It's just integral multiples of HF as an amount of energy is what quantized is about. Actually, it's sort of proportionalized in this case because it's proportional to frequency, and frequency could be anything. So they do this beam split experiment, and they measure. Now, I'll show you the results, but here's the difference. I do the experiment with gamma rays instead of visible light, and I get the opposite result. I'm showing that it can go to two detectors more often than accidental chance. So it's about comparing to chance to know whether it goes one way or another, like quantum mechanics, or if I can split it and defy quantum mechanics. So we're going to be talking about the chance equation and such. Anyway, so that's the experiment. Now what I'm doing is a little bit different. I'm going to draw the experiment where here's the source, and there's a beam splitter, and there's a detector and another detector, and it goes to an oscilloscope where there's two pulses. Okay. Now I've done this experiment in all variations of the experiment. I've used 5 different detectors and different sources, radioisotopes that put out different gamma rays. I've done it hundreds of times in scores of different ways. But the particular version I have here is that it's a thin detector in front of a thick detector. So there could be a detection here and here to make those pulses. It's just a way of combining the beam splitter and the detector into one element, and it makes the experiment work better. faster. But it's essentially the same thing as a beam splitter. So I'd like to zoom in on just what this experiment is. We're going to try to zoom now. So this is a radioisotope of, it's surrounded by lead with a little hole in it. It's putting out gamma rays. It's perfectly safe. You could just buy it. So this is the thin detector, and then the thick detector after it. And there's actually another step here where there are pulse height filters here, where the pulses that come out, they have to be within a certain range. If they're too small, I don't count them. If they're too big, I don't count them. So that's what all this is on the bottom. There's amplifiers and pulse height filters. So I'm only counting the valid pulses, and that's a perfectly valid way to do it. In fact, I'm bending over backwards in favor of quantum mechanics to do that. So that's essentially explaining what the components of the experiment are. And so we look at these pulses, and there's this great big peak that on the oscilloscope I'm going to explain. So there's timing in between these two pulses that happen, and that graph it's called a difference in time graph, and there could be 0 in the middle, and it's the number of coincident pairs that happen. And so if it goes click click, it'll make a notch there. It'll be a bar graph, a histogram. If it goes click click on the other way, it'll make a, if it goes together, it'll start building up in the middle. So you start to see these coincidences that build up, and so it makes a histogram, and you get to see the profile of how close together the pulses are. And we're going to count how many pulses happen in a given time range. I'm going to give that a symbol. And it's 200 nanoseconds. So we're only counting what's in, you can see the cursor lines on the scope. That's where we're counting. And it says TOT peak, the total peaks points. That's how many pairs there are. 2,400 points. And then DUR, that's the duration, 4.6 kiloseconds. So I can read the number and the time and get the rate. And that's how many coincident pairs are happening. So I can read that off the oscilloscope. So there's an equation for chance. And it's the chance rate. You read the rate in one detector and the rate in the other detector times this time window. You multiply that together, and I just did that a little bit earlier today, and we get some number. That's what should overlap by pure accident. And if I take the source away, you'll just see a bunch of well, there are coincidences that are happening by cosmic rays, and you have to subtract that, and I do. So earlier today, I took the source away, and I measured the background rate. I got some number. And so when I look at what comes out of the LaCroix oscilloscope, I get so many per second. I subtract background. and I get a number. It's about every 2 seconds I'll get a coincidence, which is great. So that's my experimental rate. So I compared the experimental rate to the chance rate. So I calculate out the chance. I'll read what I just said about first detector and second detector, and I get some number. And I take the ratio of those. And this experiment is happened to be running at almost 15 times chance, which is great. No one's ever done better than 1. All the other experiments, when they take this ratio, they get 1, which means chance. No one's broken chance. This breaks chance. I'm saying a particle did not have to exist ahead of time to make the detector do what it did. Otherwise, it would be violating energy conservation. I'm saying there had to be some energy there ahead of time, and then it gives a click to give the illusion. It gives a pulse that makes you think a particle hit there. That's the resolution of the wave-particle paradox, to understand that there are thresholds and then sudden releases. And that's the only way to interpret this experiment. Otherwise, you're getting 2 for 1. 1 comes out at a time, and then 2 happen undetected. Well, how are you going to get 2 for 1? That's what it's about. In order to get 2 for 1, there had to be something there ahead of time. For something to be there ahead of time, it means it's loading up. So I'm demonstrating the loading theory. No, and I'm doing it the same way other people have looked for an alternative to quantum mechanics. Let me show you that. Here's the first time they... You won't be able to see it. It doesn't matter. I'm just trying to show you that there was a paper done at some year. They did it with X-rays in this case. This was 1946. Then in 1956 they did it, and that looks more like a beam splitter. So they used the same chance equation, and they admit that if there was some correlation, if you broke chance, you'd have to rewrite quantum mechanics. They admit it right there in Nature, this Nature magazine. Now, this is Physical Review, and it's hard to see that I could blow it up, but this is their data. There's no peak there. They're doing it the same way I'm doing with this time difference histogram. They're just getting a bunch of noise. There's no... So I'm doing the same kind of experiments, same kind of electronics, the same equations, except I'm doing it with gamma rays. They're saying, since there's no correlation, since it looks like noise, it has to be a photon. And I'm saying for the first time, it can go both ways greater than chance. Therefore, there are no photons. So I'm playing by their rules. I'm showing you these past experiments. There have been many of these attempts. Here's another one. The French team did it a little bit later. That looks like a beam splitter, doesn't it? It's the same experiment. And they say the same thing. Well, they say, well, gee, it definitely one way or the other, just like a photon did, therefore it's got to be quantized and it's a photon. And then it's written up again, the same kind of this. And then there were patents granted on those experiments, and that's where they get the idea of quantum cryptography, where they think that you can't tap off a little bit of energy because physics said you can't do it. You can't tap off a fraction of a photon, they say, because it's a photon. But I'm saying no, that'll never work. It's never worked, by the way. They say it works, but they're doing all kinds of tricks with quantum cryptography. there are whole societies of quantum cryptographers, by the way, and they're not going to like me. So, in the meanwhile, there are many ways where somebody can say, well, maybe there's some error in what you're doing in this experiment. How do you know cadmium-109 only puts out one gamma ray at a time? Well, for one thing, the nuclear physicists say so I get this information off the web, but I also tested it. The way you test it is you put two detectors face to face, and you put the radioisotope in the middle, and you see then if you get coincidences on your oscilloscope like I do. And you don't. There are no coincidences. It only goes like ding, 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 one to the other. You don't get, so you know it only puts out one at a time that way. And that's how everybody says it, and it makes sense to me that that's true. So we know we're dealing with a one-at-a-time type of source. And then after cadmium-109 decays, well, maybe does that make another gamma ray? No, they tested that. And that's what this other numbers are that you can't see, which it says it turns into silver-109, which is stable. And so then I kept doing all kinds of variations on the theme. I was building this lead shield because there's some interference from outer space. I wanted to make it very quiet. So we did this tremendous effort to build this 1 foot wide lead shield and do the experiment inside. And it was like a factor of 30. It was 1/30th of the background. It worked well. And so I did a lot of experiments inside this lead shield. And that's a picture of my laboratory. About what year was that? 2003. So I've been doing this for over 10 years and telling people about it. An early demonstration version I did, same here. And here's inside the lead shield, the two detectors, different detectors than what I have now. So, and then I used the liquid nitrogen cooled detectors, really great detectors. So, and there's all variations on the theme. This is an interesting plot. If it can split into two, why can't it split into 3 or 4? Well, I was able to see that. So in one detector, it triggers it. And the other detector, if it gets 2 at a time, it'll make a pulse twice as big. And this graph is on the horizontal is how big. So I get to see bumps in it that say we're getting 2 at a time. So this bump is 2, this bump is 3, and this bump is 4. So it does split up like that. It's the loading theory. It's filling up the last bit of something preloaded. So it just takes a resonant absorption. It doesn't have to have the whole photon's worth of energy. It just needs a little bit. And then it could make it all go. Give the illusion that a photon hit there. And then I did many variations on the theme, experiments showing that this unquantum effect is a useful measuring tool. The beam splitters were different materials, and by changing the angles, I was able to see crystallographic effects. So it was a useful method, and I tried to file a patent on it, but the patent office looked at everything else and said, oh, gee, this can't be, and rejected it. Even though I gave them like 20 experiments worth of data, my strategy was to overwhelm them with data. And what they said there was no data. So there's just no making sense out of them. So I have a thing about the patent office. All right. Now I'm going to talk about a slightly different experiment, because to resolve the wave-particle paradox, you have to understand what's happening both with light and matter. So I went ahead and tried to split the atom like a wave in the same kind of experiment. So I took a smoke detector apart and got americium-241, which puts out an alpha ray, which is the helium nucleus. I like calling it the helium nuclear wave function, because I went and split the helium wave. I split helium like a wave to go to 2 detectors and read this coincidence effect. And it worked amazingly well. What I have is a gold foil in front of one of the detectors. So usually the alpha ray will just go one way or the other. It'll go to one detector through the gold foil, or it could bounce off the gold foil to the other detector. But sometimes it'll split and go to both at greater rates than chance, which it should not do if it was a particle. They call it the alpha particle. And so I'm able to measure 200 times chance in this experiment. And so I thought, well, gee, that's pretty cool. Well, oh, by the way, maybe I'm splitting the alpha ray or splitting the atom into neutrons and protons or something. It turns out it takes more kinetic energy than what I'm using to do that. I'm at 5.5 million electrons volts of kinetic energy, whatever that is, some number. It takes like 14 to split it. So there isn't enough kinetic energy to split it into protons and neutrons or deuterons or anything. And that's by other people's work that they do these tables. And so it looks like I'm splitting the atom like a wave. And it makes sense because there are other experiments that show atoms diffract. They've done helium diffraction experiments as far back as 1930. And they can diffract what they call electrons and protons and neutrons. All those, what they call quantum particles, have this duality. So I did this experiment with the matter wave to split it in a similar way, so I can talk about resolving the wave-particle duality paradox for both matter and light. Well, I hardly believed it, so I went and built the experiment, like in this vacuum chamber, then in this vacuum chamber, then I rebuilt it in this vacuum chamber, and then rebuilt it again in all different ways. I just kept rebuilding it and thinking, well, gee, is there something I'm doing wrong? And there's nothing wrong. I did all kinds of tests and measurements. It kept working. And I even put the whole experiment inside of another detector to make sure it wasn't outer space affecting it in some way. I would pick it up. So I want to make sure that we have some understanding of the experiment. If there's any questions about the experiment. It's not easy material. You could very easily not understand. So there's some theory, a little bit of theory, I'd like to just touch upon quickly to make it more understandable. Because I did the theory first, and then knew that the experiment would work. If you look at the photoelectric effect equation, and this experiment is mostly, it is about the photoelectric effect. That's what's happening. Light going in and emitting an electron. This is a photoelectric effect experiment. So we're going to write down the photoelectric effect equation. So it's Planck's constant times frequency is equal to a kinetic energy, which is mass of the electron times the velocity of the electron squared divided by 2. Now, Einstein came up with this, but there wasn't any derivation. It was just that he realized, oh, well, gee, HF, that's cool. Planck did that. He did a whole big argument about saying, oh, let's use HF. And then he went and used it and said, oh, well, let's use the particle model and just write down HF equals 1/2 mv squared. So there really wasn't any derivation for the photoelectric effect. But if you look at my work, you'll see that there is a derivation for it. What I did is I linked it to another equation, the de Broglie equation, which is a wavelength equation, which is that Planck's constant is equal to mass times the velocity times the wavelength. And I had a simple way of deriving one from the other, just using velocity equals frequency times wavelength and a factor of 2 correction. And I don't really want to bore you with it, but you could see it on the web. And so I did what essentially is a derivation of the photoelectric effect equation. What I want to point out, though, is an interesting trick in these equations. If you put the mass on the other side, just do that. Now, Planck's constant is a measure of action. The action to mass ratio is what we'll measure in the photoelectric effect. We don't measure in the photoelectric effect experiment H or M individually. We measure the ratio. So we measure the velocity, we'll measure the frequency, and then we'll see the H to M ratio. And then there are other experiments that have these ratios that are famous for wave-particle duality. So what I'm saying is that if you look at a wave and take a piece of it, some volume, you might have 1/100th of action and 1/100th of the mass there, but that 100 cancels out, and you'll have the H to M ratio. So it's this simple ratio trick that lets you see how the wave can work. Otherwise, when you go to school and learn all this, there'll be these little m's there, and they'll say, oh, well, that's the mass of the particle. Well, it's not. It doesn't have to be the particle because it's in a ratio, and there could be less. You don't measure the whole m in those experiments. They're different experiments. The experiments that are famous for wave-particle duality, I could write a few of them down. There's a Compton effect equation, which is a change in wavelength. Lambda is equal to h over mass times the speed of light, and there's a 1 minus cosine theta. Doesn't matter. It has this h to m ratio. So there's an experiment that had. Then there's another experiment. There's the Lorentz Force. There's force is equal to mass times acceleration, which is equal to the charge times the velocity times the magnetic field. If they're right angles to each other, well, you just do this. You put the E on the other side, the mass to E ratio. the mass to charge ratio. And you'll see it doesn't have to be done with particles, because you don't measure the individual mass or the individual charge in those experiments. You measure all the other stuff in those experiments. So you get to see the message of the experiment without wave-particle duality by just understanding how to set up your ratios, and that the constants are about maximums. There are such constants. There is a charge constant. There is an action constant. But those constants are about the maximum values. And when we look at our experiments, they're in these ratios. So that's the essence of my theory. And I don't know if you understand it or not, but I wanted to get it on the video at least. And once you see that, then you could say, oh, well, gee, it's possible to do this without particles. Otherwise, it just looks kind of nutty. How can it possibly be? You have to take this conceptual leap and say that these constants that they're so sure are constants are just maximums. But there's nothing wrong with doing that, because they all come out in ratios in our famous experiments that are in wave-particle duality. There are a few more, but I don't have to write them down. So everything I'm saying is on the internet, and I would love it if you were to look at it and send me an email and say, oh, Eric, what do you mean by this? And you could call me up or visit me. Say, well, let's look at it. I'm trying to make friends here. And alliances is why I'm going out and showing it in public. And I've tried talking to physicists, and invariably they just say, well, there must be something wrong. Well, somebody else has to reproduce this. Of course, I know somebody has to reproduce this work, but there's nothing wrong with it. Well, tell me something wrong. Nobody's ever found anything wrong. I've been telling physicists about this for 10 years. They try to take pot shots at me, but nothing holds up. So I think I went through all the material. I think I went through all my material. Amazingly enough, I went through the theory, that's sort of how I look at the wave. It's about beats. I use musical principles. The link to music is that I built musical instruments and I drove energy into the musical string, and I was able to see this threshold effect that I'm talking about. And there's a difference frequency effect that I use with beats, and I use the equations of beats in my physics. So the musical instruments that I built and the experiments that I've done with them told me about the world, how physics should work, and get around the wave-particle paradox. Please, are there any questions?